So I'll give an overview presentation on recovering of biopolymers from wastewater with the motto, are we ready for business or not? First of all, a few words on WETSUS. Not all people might know WETSUS. I work for WETSUS, which is a Dutch research institute for water technology. We perform PhD-based research to develop radical new water technologies, and we act as an intermediate between companies and universities. On average, we have 50 to 60 PhD projects running in a year, and we have more than 100 companies that support our research. And of course, one of these research topics is the recovery of biopolymers from water. And that is what I will be presenting today. So if we look at organics in wastewater, the traditional way we are treating them is basically we burn them or aerate them biologically and remove them from the wastewater and transform them to CO2. In some sewage treatment plants or industrial wastewater operations, part of the organics are also transformed into biogas, which we can then use for energy recovery, electricity, or heat production. And that's how we've been doing for the last decades, but we think we can do that better by moving to transforming these organics into more valuable biopolymers. And that's what this slide shows. Also compares the value of different biopolymers that one could recover from wastewater and compares them to the value of methane. So if you look at methane, so biogas, the value would be roughly 0.08 euros per kilogram of COD that is contained in this methane. But if you would recover a biopolymer like PHA, which I will explain a bit about later, or cellulose, then you see that the value is significantly higher than when you would be able to make biogas. So there's a huge business opportunity here to recover biopolymers instead of making biogas. Of course, there's some buts. The value is higher, but also the cost to make them will be higher. And also there might be differences in yields. So that's something to look into when you make your business case. But on the other hand, also this higher value shows that society apparently values these biopolymers much more higher than making biogas. And that's also what you see in the value pyramid to the left, that you see, which often used to motivate that, yeah, it's nice to make energy, but in a society, we also need to go make the higher value products. And that's where the bigger business is. So that's the vision behind making biopolymers from wastewater. But the next question is, of course, then, is there relevance in the amount of organics that are in wastewater to really be able to make a business impact? And this slide shows a graph that's made by Nova Institute as part of the Renewable Carbon Initiative. The Renewable Carbon Initiative is a big corporation of a lot of companies, big multinationals like Lego, for instance, that have presented a vision on how the European Union could transform into a more zero emission in the chemical industry in 2050. And what the slide shows is that already in 2020, 8% of the chemicals and materials that we use in Europe are bio-based. And the total amount of carbon in these materials is 550 megatons. And so 8% of that is 44 megatons as currently in bio-based materials. If we look at the carbon that would be present in the wastewater of municipal wastewater and industrial wastewater, then we're looking at a value of 10 to 14 megatons of carbon that is there present. So we could, in the current situation, we could replace, in theory, 25% of all the carbon that's now already being used in bio-based materials. And if you look to the future and in the vision that they present, then they think in 2050, roughly 230 megatons of carbon would be required as bio-based materials. So that also shows that there's a huge increase in demand of bio-based carbon. And that will also mean that we need to use all the carbon that is there in the best possible way. So that shows that, wastewater is a significant part, maybe not the most significant source of carbon, but it is a significant source. So there is potential to recover carbon and transform it into materials. So what biopolymers could we then recover from wastewater? I will now give 3 examples of biopolymers that are quite far in their development that you could recover from wastewater. So the first biopolymer we can recover are cellulose fibers. Cellulose, it's basically paper. And this cellulose comes from toilet paper that we're flushing through the toilet. And this can be sieved out in the sewage treatment plant. And it represents roughly 20 to 30% of the carbon load of a sewage treatment plant. So a significant amount of the carbon is contained in these cellulose fibers. And already there are several installations in the Netherlands and also in the UK where this has been demonstrated at full scale that you can recover these fibers from the sewage and then also wash and upgrade them to a quality that has a market. Another substance that we can recover is our extracellular polymeric substances. So that's a complicated name, but it is a sort of a container name for the stuff that makes sewage sludge jelly. So sewage sludge contains a lot of water, and it's very difficult to get that water out of the sludge when you try to dewater it. And these extracellular polymers are the reason why they bind a lot of water. There's a lot not known about this dark matter, although there's a lot of research that's been done the last decade, so we're starting to know more and more. But what we know now is that these polymers that these bacteria make are very unique polymers that are made up of sugar and protein monomers. So they have unique properties that you cannot easily make by yourself. And for instance, they can be recovered. That was the first idea. They can be recovered from aerobic granular sludge, but they can also be recovered from traditional flocculent sludge. And so that also makes it applicable both for municipal and industrial wastewater. And the way you have to do this is to have a mild alkaline and acidic extraction, and then you can get these polymers in a relatively pure form. And that you can then transform into products. And Delft University, Mark van Loosdrecht and Yuman Lin have done a lot of work on this development. So there's a very good theoretical knowledge about what is there and what we could do with that. And at WETSIS, we're also doing a lot of work. Carlos Contreras Davila at WETSIS is doing a lot of work on trying to transform these EPS polymers into, for instance, flocculants. And third polymer that we could recover is PHA. PHA is short for polyhydroxyalkanoate, but you could simply say it's nature's polyester. So the polymer looks very much like the fossil-based polyester that we make, but it's made by bacteria. And for the bacteria, for them, it's a sort of an energy reserve that they make in periods when they see a lot of carbon around. They just try to get all these beads together and they make this polymer. And we can recover that from this biomass via a solvent-based extraction. And then once it's been extracted, we call it Kaleida. And again, Delft University, Mark van Loosdrecht again, and Robert Klerenbezem of Delft have done a lot of research on this. So we know the basic principles. And also at WETSIS, Anna Worker from WETSIS has been working on this for more than 15 years already to understand how we can tweak and tune these polymers. So, okay, we can make these polymers, but what is their unique selling point to compare to bio-based polymers that are already on the market and also fossil-based polymers? And that's a bit shown in the picture to the right. On the bottom left corner, you see the conventional plastics. So they are fossil-based and they're not biodegradable, which creates a lot of problems in nature at the moment. Then when you go to the right, the polymers become more biodegradable. And when you go to the top, the polymers become more sustainable. So you don't want to make them from fossil resources. If you go a step higher, you can make them from agriculture, from materials you grow in agriculture. Of course, there you have the downside that you have a competition with food production, which is also sometimes not considered very nice from bio-based materials. But when we recover it from waste, we have a very unique selling point, which is that it is a very sustainable material because it's wasted anyway. It's very low quality, and if we can transform that in a very high quality product, yeah, we've done the best we can do in a circular economy. So that's where we have our unique selling point. And also the degradability is very unique. A lot of bio-based polymers that are now on the market are biodegradable, but only in the industrial composting installation. They won't be easily biodegradable, and they end up in seawater or in nature, whereas these nature-based biopolymers are really readily biodegradable in even marine seawater. So nice ideas, nice concepts, and a lot of solid research has been done. Also, a lot of pilots have been done. But then the next step, of course, has to be made. How can you get into business to really build a value chain for these polymers? And that's where we basically are at the moment. Recently in May, we had a big conference in Leeuwarden in the Netherlands with the whole community of resource recovery from wastewater. And the whole concept of that conference was, how can we go from concepts to real business models? So that's where we are as a sector now looking at. And a lot of lessons has been learned. And when you look at these lessons, you could say that this is a list of the lessons that we learned. So often we focus on the product value, but often there's also a value in just if you transform it and we remove it from the wastewater, you have other advantages that, for instance, you need less aeration or less maintenance. And you should also take that into account to get to a viable business case. You should, of course, be tuned. You should not be happy that you make a product. You should really make a product where there's a market for and find the market need and the niche where you can get your product. What you often see is there's a chicken and egg situation that, well, the customers are interested in a product and they need quantities, but the quantities are not there because the investors first want to see demand for the product before they invest in making quantities. So that's what you have to circumvent by trying to scaling up slowly and slowly by creating more volume in time. Finally, end of waste status is an important issue because there's a big yuck factor when you recover something from waste. But we are learning how we can show that the product that we make is sustainable, doesn't contain any toxic components anymore, and how we should address that also to the legislator, because the legislator is a bit backwards, so and not very slow. So the way to go is what we learned now is that you should go to a self-declaration to build your own dossier, show that you have everything under control, and in that way declare end of waste for your product yourself and not wait for the legislator to say it's end of waste. And finally, a lot of these carbon materials in wastewater come from public water authorities, and the public water authorities are very interested in making high value products, but they're not very good in selling them. So you need an entity that bridges the public sector to the private sector, and in the Netherlands we've learned how to do that, and the Dutch water authorities have created a new entity which is called Aqua Minerals, which acts as basically the sales department of the public sector. And we can see that commercialization is actually taking off in the Netherlands, also for these three polymers I've been mentioning. So, for instance, for cellulose, the Surtec company, which is a subsidiary of Nijhuis Water Technologies, can build and deliver full-scale installations to recover the cellulose from your wastewater. The company Resell has specialized in upgrading this recovered cellulose and making it into products and finding markets for it. The same you see for the EPS-based polymers. Comera is an entity that has been founded by the Dutch water authorities in cooperation with Haskoning, a big Dutch consultancy. And they have two bigger scale installations where they're already producing this material for business. And we will also have a presentation from BioFire later in this webinar that can transform this EPS into flame retardants. And finally, PHA, we have the company called Parks Biomaterials, which has grown, I think, in 3 years from 2 employees now to roughly 20 employees, which we'll also have a presentation about in this webinar. And they built an extraction facility in Emmen in the Netherlands and tested it at large scale in Dordrecht. So you see also there that traction is there. We are ready to go into business there. And what is the role of Vestas in this whole development? So we are, of course, a research institute. So together with the industry and our academic partners, we generate new ideas. So what could we do? And test these ideas and maybe see if we could, for instance, make a fertilizer out of certain components. We help to understand the underlying basic principles. We can optimize the yield or the quality. And of course, very important, we train the next generation of engineers that are trained in making these biopolymers and also looking what their role should be in a bio-based economy. So that's my presentation. So as take-home messages, wastewater is a relevant source of bio-based materials. Currently, we see cellulose, EPS, and PHA as the most relevant recoverable biopolymers. And we are now past the phase that it's really exciting that we could maybe potentially do that. We are actually doing it and getting into the business phase of this recovery process. And the sector is therefore ready for commercialization. Of course, we still see challenges, but there's a huge benefit and potential up ahead. So let's work on it together to get it realized. That's my
very nice. Leon, thank you very much for this overview presentation. Thanks. You even get digital applause, I now see here in the screen. Maybe for now you want to stop the slide share so we can see you a little bit bigger in the screen. Excellent. There's some questions coming in from Thomas already, but maybe first to start off, Leon, I think you now have about 20 years of experience in this field. Do you now finally see this momentum coming up? Because so much has been researched over the years, and I think it also is due to policy and also business, I don't know, factors like energy pricing. But do you finally see the ball moving into the right direction, so to say?
Yes, yeah, I have good hopes that we are getting there. And I think, the examples I showed of the businesses that are really getting traction at the moment, I think that's the best evidence that we are getting there. And they're also attracting investment money. So that also shows that the investor community is ready to make a next step. Of course, there's still important bottlenecks. We see that legislation is lagging behind a bit, so we need to push them to adapt. And we also see that stimulation is a bit, there's not a level playing field. For instance, biogas gets a lot of subsidy. The value for biogas that I showed in the slides earlier is without subsidies. But it is, I think that's a factor 3 or 4 over it, if you would take into account the subsidies that are put onto biogas. Whereas if we would recover biopolymers, we get 0 subsidy at the moment. So that's another level playing field.
No, there's some big differences. Yeah. So if anyone of you has a question, please feel free to type it in the chat or simply raise your hand and